So this is a continuation of Logistic Regression Part 6. Today I will discuss goodness of fit. Before discussing goodness of fit, first we define saturated model. A model in which we have a different parameter per observations. The fitted values are equal to the observed value, and the residual are all zero. Since the residuals are all zero, the saturated model explains all variation by the systematic component of the model. The saturated model has a separate parameter for each observation. It gives a perfect fit. So this sound good. So this sound good, but it is not a helpful model. It does not give or it does not smooth the data. It serves as a baseline for other models. Such as for checking model fit. Suppose yi follow Bernoulli with parameter pi I, then estimate of pi I for the saturated model is pi I hat equal to yi 1 if yi equal to 1, 0 if yi equal to 0. So pi I hat takes either 1 or 0. Therefore the likelihood at the MLE for the saturated model equal to product of I from 1 to n. Suppose we have n observations, then this is equal to pi I product of I from 1 to n pi I hat to the power yi 1 minus pi I hat to the power 1 minus yi. This is always 1. Why? See, yi take two value either 1 or 0. If yi take 1, then it should be 1 to the power 1 into 1 minus 1 to the power 0, that should be 1, because 0 to the power something to the power 0 is always 1, so this gives 1. And when it is 0, then again similar reason, 0 to the power 0 into 1 minus 0 whole to the power 1 minus 1, 1 minus 0 again 1. So this product should be 1 always. Hence the product of I from 1 to n pi I hat yi 1 minus pi I hat 1 minus yi should be 1. Therefore, likelihood at the MLE for the saturated model equal to product of I from 1 to n1 is equal to 1, and this imply log likelihood equal to log of 1 equal to 0. Suppose even if the underlying data are coded as Bernoulli for your computer program, that in reality the underlying data actually arose as product binomial. That is, many subjects have the same explanatory variables or same values of the explanatory variables. That means suppose I divide whole n observation into k groups. First group consists of n1 subject, n2 subject, and kth group consists of nk subject, and these subjects take same covariate values or values of the explanatory variables. Similarly, these subjects into subject consist of another same covariate values or explanatory variables, values of the explanatory variables, and so on. So that is why I tell that the underlying data actually arose as product binomial. In particular, suppose the underlying data are actually made up of I binomial for here I say instead of K I write it I group, capital I group. Capital I group. So first group consists of n1 observations, second group consists of n2, and last group, that is ith group, consists of ni observation, such that sum over ni I from 1 to capital I equal to small n is total number of observation. Therefore, in particular, suppose the underlying data are actually made up of I binomials, that is, for this yi, y1 follow binomial n1 pi 1, for this y2 follow binomial n2 pi 2, and this one yi follow binomial ni pi I. So suppose the underlying data are actually made up of I binomials, and there are ni subject with the same covariate vector xi called covariate regressor explanatory variables are synonymous. So with the same covariant vector xi, curl I from 1 to capital I, then y1 follow binomial n1 pi 1, y2 follow binomial n2 pi 2, and so on. Since the product binomial and product Bernoulli, the product Bernoulli and product binomial likelihoods are proportional. Why? This is for this is called product Bernoulli, and this is simply as and since these values take same covariant values, so I write it like that: I from 1 to capital I, and this portion, because this takes the same covariant value, so this portion should be pi I to the power capital y1 yi should be capital yi actually I write it in that way, it is better. Say for yij, this is for jth response from ith group. Then this is I from 1 to capital I, j from 1 to ni, pi I yij 1 minus pi I 1 minus yij, this is equal to I from 1 to capital I, because for this group pi I fixed, for this group pi 1 fixed, for this group pi 2 fixed, and for ith group pi I fixed. So basically if pi ij is pi I for ith group, so instead of pi ij I write pi I. So I from 1 to capital I, pi I sum over yij into 1 minus pi I ni minus sum over yij, and this is nothing but a yi, because for ith group this yi, because sum over yij is equal to number of success or number of ones in ith group. So this is simply yi, and I already mentioned that yi, capital Yi denotes number of success or number of ones in ith group, and it follow binomial ni pi I. So this should be yi. Similarly, 1 minus pi I equal to ni minus yi. So this is called product Bernoulli. This is called product Bernoulli. Similarly, if I consider instead of Bernoulli distribution, if I consider binomial distribution, then this is same thing except this combinatorial part. And this is called product binomial. Since the product Bernoulli and product binomial likelihoods, this is called product binomial likelihoods, and this is product Bernoulli likelihoods. So the product binomial, product Bernoulli and product binomial likelihoods are proportional except this combinatorial part, which does not depend on NICYI. So instead of pi I should be yi. So instead of this should be yi. So this is the product Bernoulli likelihood and product binomial likelihood are proportional except for combinatorial term, that is NICYI, not depending on this term, not depending on beta curve. So we would get same MLE and standard error estimates. However, for goodness of fit, we would use product binomial likelihood with xi curl covariate vector associated with group I, and we want to test the fit of the model M1 logit pi I equal to xi curl prime beta curl, where xi curl equal to 1 xi 1 xi k. Since we consider k covariates or k explanatory variables, this should be prime, and beta curl equal to beta naught beta 1 beta k prime, versus saturated model, in which we estimate a different pi I for each I. This is our claim, or this is our research question. Since we consider binomial distribution instead of Bernoulli distribution, so for saturated model, pi I curl, estimate of pi I is equal to yi by ni instead of yi. Why? If we take Bernoulli distribution, then pi I curl equal to simply yij, and this is true for ith group, because for ith group pi I is fixed, so this should be this, and this is nothing but a yi, so pi I curl is equal to yi by ni. Now, log likelihood function of beta curl given y curl, this is our log likelihood of beta curl given y curl, and this is a maximized log likelihood for model M1, and this is maximized log likelihood for saturated model. Now we consider likelihood ratio. Likelihood ratio is nothing but a maximum likelihood for M1 by maximum likelihood for saturated model. Since we know likelihood ratio statistics for testing the null hypothesis that the model holds against the alternative that a more general model holds. That means supremum of theta naught L theta curves by supremum of theta naught union theta 1 L theta curve. So this is under H naught and this is under H naught union H1. Now the log of log likelihood ratio is equal to log of L beta curl hat y curl. This is maximum likelihood for model M1 by beta curl tilde y curl. This is maximum likelihood for saturated model, and 2 minus 2 into log likelihood ratio minus 2 log likelihood ratio equal to minus 2 is equal to 2 log L beta tilde y curl minus log beta hat curl y curl. Now if we ignore combinatorial part, then this should be product of I from 1 to capital I pi I hat yi 1 minus pi I hat ni minus yi log of this. So we write it sum over I from 1 to capital I yi log pi I hat plus I from 1 to capital I ni minus yi log 1 minus pi I hat. And similarly this part equal to I from 1 to capital I yi log pi I tilde, which is nothing but a yi by ni. So this should be yi by ni plus I from 1 to capital I ni minus yi log 1 minus yi by ni is nothing but a ni minus yi by ni. So therefore this is equal to L beta curl y curl minus L beta hat curl by beta hat curl given y curl. So this is equal to 2 into sum over I from 1 to I yi this minus this, so I write it this minus this, so I write it yi by ni pi I hat plus 2 into, I take 2 outside of this bracket, so I from 1 to capital I ni minus yi log ni minus yi ni 1 minus pi I hat. Now denote ei1 equal to ni into pi I hat, ei2 equal to ni into 1 minus pi I hat, oi1 equal to yi y2 equal to ni minus yi, then this term simplified as sum over I from 1 to capital I, sum over k from 1 to 2, O I k log O I k by E I k. So 2 into sum over I from 1 to I, capital I, k from 1 to 2, O I k log O I k by E I k, and we denote this by d square m1, and this is called deviance. Deviance d square m1 is often used as measure of overall goodness of fit and is a test statistic from terms left out of the model. We see that d square m1 approximately chi-square with p degrees of freedom when ni tending to infinity. And p equal to number of parameters in saturated model minus number of parameters in M1. For deviance, d square can be used as statistic to measure the fit of the model, and you need, already I mentioned that you need for this ni tending to infinity. We can use alternative test, that is score test or Pearsonian or Pearson's chi-square goodness of fit. For a given model versus the saturated model, where the test statistics is I from capital I yi ni pi hat whole square by ni pi hat 1 minus pi hat is equivalently written as I from 1 to capital I, k from 1 to 2, y k minus eik whole square by eik. Again this follow chi-square with p degrees of freedom. So please stay with us. We will continue this topic logistic regression in our next class. Thank you.